Hello everyone, I am Radha Kumari Pani, Assistant Professor at VIT. So in last class, we have discussed about the Clausius-Clapeyron equation and the formula was dt by dp that is equal to del v by del s. dt by dp is equal to del v by del s. Okay, where v is the change, del v is the change in volume and del s is the change in entropy. And this formula has a very significant role in like phase change in phase changing system, like in water system we have seen the diagram. Okay, in water system from solid to liquid, that is melting, and from liquid to vapor, that is boiling, and from like solid to vapor, that is like freezing, that one like that. So how the formula dt by dp is changing according to their volume, according to their entropy changes. Okay, so in today's class, we will be going to discuss that is carbon solubility in iron, which is a very like important role in daily life. Carbon solubility in iron means, in simply words, we can say in which structure of iron the carbon concentration is more. Okay, generally we'll consider the two structure here of iron. One is that is alpha Fe and another one is gamma Fe. Alpha Fe, or we can say the BCC, that is body centered cubic close packing structure, and another one is that is gamma Fe, or we can say FCC, that is face centered cubic close packing structure. Okay, from first class we have discussed the how the like CCP structure, cubic close packing structure, how the Bravis lattices. Okay, there are 14 Bravis lattices in 7 system. So generally in BCC means the lattice point. Okay, like in Fe, the lattice point is generally present in all over the corners, like we have 8 corners and one is body center. Okay, this one is BCC. Similarly, in FCC structure, the iron atoms are present in all corners and all 6 face centered. Okay, so first, solubility of carbon in Fe means it is the function of structure and temperature. Okay, on two things it will depend. First one is structure, in which structure the carbon solubility is more, and another one is, that is the parameter, is temperature. Okay, we'll see. So here the white one, okay, the white ball are Fe, that is iron atoms. In BCC structure, the iron atoms are present in all the corner, that is we have 8 corners in cubic close packing and one is that is body centered. And the rest of that, like in edge centered, okay, we have 12 edges in cubic close pack structure and 6, these are face centered. In 6 face centered and 12 edges, let the voids are present, in which the carbon atoms will be present. And the second one is that is FCC, face centered cubic. The white ball bar iron atom that is present in all corners and 6 face centered, and the rest of the point, like the void, will be covered by carbon. So see, in calculation we'll see how the lattice point are calculated here. First, like in the 6 face centered sharing with 2 sides means each face. Okay, in cubic close packing, see, in a crystal system, small unit cell, cubic unit cell are there. Okay, from one cubic unit cell we have known one corner. Okay, one corner will be shared by 8 corners of another unit cell, and the one side, okay, one side of cubic close packing will be shared by 2 unit cell. Similarly, the 6 facets sharing with 2 sides means 6 by 2 will be 3, and the 12 edges, the 12 edges will be shared by 4 sides, that is 12 by 4, that is 3. The total lattice point or the total site will be available for carbon, that is 3 plus 3 will be 6. So in we can say the every one Fe atom we have 3 interstitial sites for carbon atom. So similarly for FCC we can calculate, let one interstitial site in center, because in FCC there is one void is present in the center. Okay, so one will be for centered and the 12 edges are vacant, so this will be shared by 4 side, 12 by 4, that is 3, 1 plus 3 is 4. In FCC every one Fe atom we have one interstitial site. So from BCC and from FCC we have conclusion that for BCC structure, for every one Fe atom we have 3 interstitial site for void, like for carbon, and in FCC for one Fe atom there is one interstitial site for carbon. Okay, So why now the concentration of carbon in BCC structure is less than FCC structure? Will understood. Okay. First, packing factor. We know the packing factor of FCC, that is 0.74, or we can say the packing efficiency, that will be 74%. Now, what is packing factor or what is packing efficiency? It is nothing. Packing factor or packing efficiency means the number of lattice point can be packed in a unit cell. For FCC, it will be high, that is 74%, and it has come from one calculation. Okay, the number of lattice point by total volume of the unit cell. And for BCC structure, that will be 68% packing efficiency, and the packing factor will be 0.6%, 0.68. So the packing factor is 0.74, means rest of the unit cell, rest of the vacant unit cell will be filled by the what? Void or impurity. We can say that is void. First, see, one unit cell is there like this. Let the lattice point will be filled by corners, like all we have 8 corners in a simple unit cell. So all 8 corners will be filled by the lattice point, and rest of the point, like one there is edge centered, we have 12 edge centered, and also we have 6 face centered. Okay, one is front face and back face, and all our rest phases will be filled by void. So if the FCC, the packing factor is 74%, that means the rest of the void will be filled by what? Impurities, or we can say, let here it is carbon. So we know that we have 2 types of void. One is tetrahedral voids and another one is octahedral voids. For one tetrahedral voids will be created by surrounding by 4 atoms, and one octahedral void, okay, will be created by surrounding 6 atoms. Remember, for one tetrahedral void will be created by surrounding 4 atoms. The space is generated, that is tetrahedral void, and the octahedral, for octahedral void 6 atoms are needed. And we know that there are 8 tetrahedral voids and 4 octahedral voids in FCC. Okay, because here the ratio of the radius of tetrahedral voids to atom, radius ratio means r plus to r minus. Okay, that for the tetrahedral void is 0.225. Okay, and for the here it is for the tetrahedral void, and for the octahedral void the radius ratio is 0.414. Okay, it has come from calculation. So here the radius of the carbon atom to Fe, that is 77 picometer. Okay, but when it has FCC crystal, see, every like radius of every atom, like to the lattice point, that is one significance point, but when it comes to some crystal, okay, the size will be reduced because of small like distortion will be there. Okay, one void is there, one impurity will be involved, so some distortion will be there, so the radius will be reduced to 0.596. So when the carbon atom occupies any void, either it will be go to what, tetrahedral void or octahedral void, there will be some distortion. Due to some distortion, the enthalpy will be increased. Okay, so because of the increasing enthalpy, now the carbon atoms also will gain some entropy, because when there is some distortion, there will be increased entropy. So which decrease the free energy, because we know that the calculation del G is equal to del H minus T del S. By increasing del S, del G will be less, more negative, that is the reaction will be more spontaneous. So now see, here is the conclusion, like calculation conclusion point, why the carbon solubility in BCC structure will be less than from FCC structure. See, we know that here the size of Fe atom in cubic close packing structure CCP crystal, the size of iron atom is 1.292 angstrom. Okay, but in FCC that will be 1.258 angstrom. Okay, note the difference, the size of the atom. Everyone has a single size, but when it comes to any crystal system or cubic crystal system, due to the changing in their structure, okay, changing in their lattice point arrangement, the radius of that atom some changes. Okay. So now in FCC structure, the size of the octahedral void will be 0.534 angstrom. We know that the size of carbon atom is 0.77 angstrom. So here, but in BCC structure, the size of Fe for the tetrahedral and for the octahedral is 0.364, 0.195. Note the difference. See, for FCC structure, the octahedral void is 0.534, but for in BCC structure, the octahedral void size is reduced to 0.195 angstrom. That is the conclusion. BCC, the size of the largest term, which can be octahedral 0.29, but for the octahedral void is 0.154. So, due to the smallest size of octahedral void in BCC, okay, the carbon atoms cannot be completely filled to octahedral void. But in FCC, there will be some approximate size, means 0.77 to 0.534 angstrom will have some approximate size. So, carbon atoms can completely filled to octahedral void of FCC than that of BCC. So, the conclusion, the concentration will be more in FCC structure due to the small difference, due to the relative size of void with respect to carbon atoms. Okay. So now here is the explanation in BCC structure. Similarly, like FCC, the packing factor is BCC. Here it is 0.68. Okay. And in BCC structure, there will be total tetrahedral voids will be 12 and the octahedral voids will be 6. So, but here the octahedral voids, the radius ratio will be decreased to 0.195 angstrom, so that the void, like the carbon atom cannot occupies, okay, perfectly to the octahedral voids. So this is the reason to find the lower solubility of carbon in alpha Fe or BCC structure. Okay, because there will be the size difference. Size difference is there. In FCC structure, the octahedral void size is 0.534 angstrom. That is quite similar to carbon atom radius. But in case of BCC structure, the octahedral void size is reduced to 0.195 angstrom. Okay, which has a large difference, so that the carbon atoms cannot be completely filled to the void, octahedral void of BCC, so that the solubility will be less. So here is the calculation. Okay, how we can find the the size and the radius ratio, how it is calculated. See, if we take the one side of cubic, okay, one side of cubic, we can see these are the lattice point. Okay, one lattice point is there. This is the cation and this is the anion, R plus, okay, R minus, like that. So these are the, in BCC structure, the total radius ratio means 4R will be 3A, because if you take, like in the triangle, we will take one side triangle is there, let this is A and this is A, this will be root 2A for FCC. But in case of BCC, see, in case of BCC, there will be body centered, one body center lattice point is there and another corner, here it is another corner. Okay, so like that. Here in BCC structure, how it's come, BCC root 3A is equal to 4R. See, in BC, if we take the BCC structure, this is from the center, okay, and this will be the lattice point of two side corner. So here it will be the total diameter, let 2R, here it is R and R. So R plus 2R plus R, that is 4R will be root 3A, because and here it will be 2A and here it will be A. By applying Pythagoras formula, what will be the hypotenuse? That will be root 3A. Similarly, in FCC structure, if we will take the one side in FCC, like this, in FCC structure, there will be, okay, here one lattice point, here one lattice point. So here it will be A, here it will be A, R, R. So by applying Pythagoras formula, 2R will be root 2A. Okay, so these are the calculation. These are the lattice point and how it is calculated, and these are the Miller indices 110, 110, like this. Okay, this is the calculation how it is come. like the radius of tetrahedral void and the radius of octahedral void. The calculation formula of previous conclusion, like why the carbon atom solubility in FCC is more. So here we can see the diagram. Now, according to the structure, we have conclusion that carbon atom will be more soluble in FCC structure. Now, according to the another parameter, that is temperature, how by increasing temperature, how the carbon solubility is increases. See, from the diagram we have noticed by increasing temperature, the carbon solubility also increasing like this. So we have formula weight percentage of carbon, that is 240 exponential of minus 77,300 joule per mole RT. Okay. So in terms of mole fraction, so here at 7 to 7 degrees Celsius, the carbon concentration in alpha Fe is maximum, that is 0.022 percentage. So by increasing temperature, carbon solubility and mole fraction of carbon will be more. So now the another topic that is important in phase transformation, that is kinetics. Okay, from here our thermodynamic concept has over, that is what is thermodynamic and what are the thermodynamics law and what is the thermodynamic equilibrium and what is the parameter like entropy, pressure, temperature, Gibbs free energy, Helmholtz free energy, and the two state equations all are over. Now the kinetics, and this is the very important term in our daily life. You have remember, like, notice one, that is term chemical kinetics, okay, in chemistry. But generally what is kinetics? See, from thermodynamic concept, we can say the reaction will take place or not. Okay, if the Gibbs free energy is going to negative side, del G is negative, that means the reaction can take place, means the reaction is spontaneous. And how fast the reaction will take place and in which like order the reaction will take place, like how long will it occur, it will be determined by the kinetics. The study, okay, generally we can say the study of reaction rates and the time it's needed to complete the reaction, that is called kinetics. And kinetics, in kinetics there is like what is different term are there. What is the rate of the reaction, what is rate law equation, okay, order, what is molecularity, and there is generally zeroth order, what is first order kinetics, second order kinetics. So in kinetics there is everyone one diagram is there. So kindly see here, let A plus BC is the reactant and ABC is the activated complex, okay, and AB plus C is the product. Some general equation I will give. Let A gives B, okay, A is reactant and B is product. From the energy diagram, this is potential energy and this is the configuration, okay. See, here it is reactant, here it is product P R, and here it is activated complex, so we can say transition state or A star. When A gives B, means here let A will give B or not, it will be come from or concluded by thermodynamics, okay. And how fast A will give the product B, what is the time, total time needed, okay, it will be given by kinetics. If we are totally understood the concept of kinetics, we can say yes, this process is carrying out by the first order or second order, the total time needed is like this. In daily life also it has very like important application, like our enzyme catalyzed reaction, our biological metallurgy process, these kinetics terms are helpful. So here is the example is given, like Fe3C, 3 Fe and 1 carbon atom, how it will give the product. Here it is activated complex, here like total activation energy, okay. We can say del H is del H is activation energy, okay. The activation energy will be more or not. If the product, see, everywhere we can see the reaction is stable or not. If the product energy is less that from the reactant, means here it is product energy, here it is reactant energy. Okay, from the diagram we can see the product energy is less from that of reactant, means the reaction is stable, the reaction is exothermic. Okay, so from the kinetics we can take one example. Let AA plus BB is equal to give C. Here it is the coefficient of A, okay, small AB and CD. Here it is reactant, here it is product, and there is one example, rate of conversion, rate of product formation, that is we can say minus dA by dt, okay, minus dB by dt will be plus dC by dt. This is the first equation from the kinetics, how we can write from a equation, that is the homogeneous equation. Okay, from homogeneous equation how we can write the rate law, and all the coefficient will be in ratio 1 by A, this will be 1 by B, this will be 1 by C, and this will be 1 by D. Okay, homogeneous reaction means the phase, all the phases are same. Like here it is in gaseous phase, only one phase. In heterogeneous means more than one phase is there. Okay, so this is the rate law equation, and here it is Na means number of moles, and J means rate of conversion, and rate of the reaction is J by V. So this is the very simplest like write down how we can write from the equation, from one simplest equation to rate of reaction. Okay, simply we can write in reactant negative symbol will be there, minus dA by dt, and the product formation positive symbol will be there, plus dC by dt and plus dt by dt. Okay, from kinetics one is there, like Arrhenius equation, that is very important in every like field. One asked question, the what is Arrhenius equation. Okay, that is mine K is equal to AE minus EA by RT. We have to remember how it has come. What is the significance of all term, what is K, what is A. Okay, so in next class we will be going to discuss what is Arrhenius equation, and lots of problem we'll do, okay, according to Arrhenius equation, and then we'll go into further to like diffusion and fixed law we'll discuss. Till then, take care, have a nice day.